maximization method. So we want to max, we're just picking x1, our utility function with respect to x1, and then we're writing x2 as a function of x1, don't forget. So c times ln of x1, natural log of x1, plus d, and now we're going to plug in, instead of x2 here, we're plugging in that rearranged budget constraint like we talked about. So m over p2 minus x1 times p1 over p2. Then we just need to take the first order condition and set it equal to 0. So our first order condition is derivative of this with respect to x1 is c over x1. Now the derivative of the second with respect to x1 is d times p2 over m minus p1 x1 times p1 over p2 equals 0. So let's just take in the derivative with respect to x1 in this second term. That equals 0. Then we can just solve. So this will cancel out with this. So now we have c over x1 is d over m minus p1 x1 times p1. And we're solving for x1 here. We're going to gather the terms with x1 and we're going to solve for it. Wish I would have wrote that line a little bit further out here, but so I'm just going to rearrange this. I'm going to kind of cross multiply is what I'm going to do. So this times this and this times everything else over here. So c times m minus p1 x1 equals d times p1 x1. Just cross multiply. I can just change that to a minus equals 0. Just moving it back to the other side. Then I'm going to collect the x1s, right? So again, I mean, we're kind of the same place we were before, but now we have like cm minus p1 x1c minus d p1 x1 equals 0. So we can move these to the other side. So cm, maybe I'm not doing this in the most efficient way, p1 x1c minus plus d p1 x1. So I'm moving these last two terms back to the other side. And then I'm just going to take out x1 here, right? So x1 times p1c plus d p1 equals cm. And then I'm going to divide both sides by this second term here, or like x1 times, I'm just solving for x1. So x1 equals c times m. I'm just going to write it in a particular way, so it's something we're familiar with, because we're going to get the same thing as before. I have c and then put m over here. We multiply, so we're dividing both sides by that. So c plus d, I guess I should have lowercase d, times p1. These are I'm just rearranging this like this. So this is exactly what we got before. Sub into budget. And we'd get x2 equals d over c plus d times m over p2. Just like we did with the other method. So that's the second, that's the unconstrained optimization. We basically put, x2 as a function of x1 directly into our utility function. We take the first order condition carefully to make sure we take this derivative carefully. And then we just rearrange and solve for x1 as a function of the prices as well as the budget. and we plug that into our budget constraint to solve for x2. Notice we get the exact same thing. Method. So we can type out or write out our Lagrangian here. So it's the utility function, which with Cobb-Douglas we could write as this. And then remember we have that extra minus lambda, and we get our budget constraint in here. Oops, minus m. We get the derivative of Lagrangian with respect to x1. We get the derivative of Lagrangian with respect to x2. And we get the derivative of Lagrangian with respect to lambda. So with respect to x1, x1 shows up here and then as well as here. So that'd be c over x1. With respect to x1 here, it's just minus lambda times p1. That equals 0. Same idea here, but now it's d over x2 minus lambda times p2 equals 0. And remember, this is just our budget constraint. p1 x1 plus p2 x2 equals m. Or minus m equals 0. That's an easier way for you to think about it. So we're going to solve for lambda. Lambda, then x1, x2. I guess these are like the optimal amounts. This is true. So these are starred. These x1s and x2. All right. So let's work over here. Though we might need to erase this and use another board. But let's add these two together. So let's rearrange these first. So if we rearrange this, we know that c equals lambda p1 x1 star, and d equals lambda p2 x2 star. Just rearranging these first two, right? We can move this over, multiply both sides by x1 star, and we get this first one. Move this over, multiply both of them by x2 star, and we get this one. We can add them, and we get c plus d equals lambda p1 x1 plus p2 x2 equals lambda times m, because this is the same as m, right? This is like by definition, this is the same as m, which means lambda equals c plus d over m. This is lambda times m. We're just going to move this m over, and we get c plus d over m equals lambda. We can sub this in the first two equations, first order conditions, first order conditions. We can solve this for lambda. So I'm going to quickly erase the board, and I'm going to sub in lambda equals c plus d over m into these first two constraints. Conditions where c over x1 minus lambda p1 equals 0, and then we had d over x2 minus lambda p2 equals 0, and we just kind of solved that lambda equals c plus d over m. So I'm just going to plug those in, and we can solve for x1, x2. So c over x1 equals c plus d over m times p1. Just plugging this into here and moving it over. In the same respect, d over x2 equals c plus d times p2 over m. And we could just rearrange these. So maybe we could cross multiply, or we can just basically rearrange it, and we're going to get exactly what we got before. if we rearrange each of these. So this is the same as before. So all these methods come up with the exact same answers. They're just different methods for coming to the same answer. So you can use that MRS condition, as well as the budget constraint. We have two equations and two unknowns. We could recast this constrained optimization into an unconstrained optimization by putting x2 as a function of x1 into our utility function and just choosing x1. We could do it the opposite way too. x1 is a function of x2. Plug that into the utility function and do an unconstrained maximization problem where you're maximizing with respect to x2. That's the exact same thing. Or we could use this Lagrangian method, where we kind of have this extra lambda and we have three first order conditions. We take the derivative of the Lagrangian with respect to x1, x2, and then lambda. We have three equations. We have three unknowns. The three unknowns are lambda, x1 star, and x2 star. We solve for lambda, plug that in to the other two first order conditions and solve for it. Got the exact same answer with all these methods.